Let's do problem 15.6, which is a good representative problem from chapter 15. In this one, we have an airplane flying this way. So here's our little airplane here, 10 miles above the Earth. And the Earth is 3,960 miles in radius, which is right. And so here's our airplane, and it's flying this way, and a satellite is above the airplane way higher, 4,800 miles above the Earth. And it's going the same direction, and it stays right above the airplane. So obviously the satellite has to go a lot faster, right? In the same amount of time, it has to go a much bigger distance because its radius is bigger. So the satellite's going really fast. The airplane's going at typical airplane speed. They tell us 500 miles per hour. That's about what typical airplanes fly at. And they want us to know, first question is, when is the plane at a latitude of 74 degrees, 30 minutes, 18 seconds. And they still do use latitude in degrees and seconds, like we learned about, problem 15.1, what the whole degrees and minutes and seconds things, they still do use that, so it makes sense they'd ask us this. So we want to know that. Now, what I did wrong the first time is you say, oh, that's how far we go. We go 74 degrees, but that's not right. The latitude of the North Pole is 90 degrees. The latitude of the equator is 0 degrees. They're saying we're starting at the North Pole. We're flying right above the North Pole. And if we go to 74 degrees, we're only going about 16 degrees, 15, 16 degrees. The picture they drew is pretty misleading. I don't know if they did that on purpose, but really we only go a small distance. We only go to right about here. Because here the latitude is about 74 degrees, 30 minutes, 18 seconds. We don't go very far, right? We certainly don't make it 45. We only go like about 15 degrees. So what is this angle here then? So that angle there is 90 minus this, which is kind of hard math if it's all in degrees and minutes and seconds. So let's change that, the 74 degrees and stuff just to regular old degrees, and then we can subtract it from 90. So we can go, so let's see, so 74, it's 74 degrees plus 30 minutes. That means 30 minutes, and you divide it by 60 to get degrees, because there's 60 degrees in a minute, 60 minutes in a degree, plus the seconds, you just divide that by 3,600. Because there are 3,600 arc seconds in a degree. So we do that, and then we get out our calculators. That's 74 plus 30 divided by 60 is easy, that's 0.5. 18 divided by 3,600 is 0.005. So that's 74.505 degrees. So that's the latitude where we got to 90 minus 74.505 degrees. It's like about 15 and a half, but not exactly. So it's 90 minus 74.505. It's 15.495 degrees. That's how far they traveled. Now, we want to know radians because we got to find the distance, this distance s that the airplane, that's the satellite, the distance s here that this airplane traveled. So call that s for that distance. And we know that the distance you go, the arc length you go, is the radius times the angle if the angle's in radians. It's just really simple. If the angle's in radians, it's this distance equals the angle in radians times the radius. So we want to change this to radians so we can use that formula. So that we multiply by pi radians is the same as 180 degrees. And degrees cancel, we know we did it right. So times pi divided by 180. And ends up being 0.2704. Well, I'll keep the 04. So 0.2704 radians. Now I'm going to write the radians so I know what we're talking about, even though with radians you don't really need units. It's the natural unit. It just gives you the answer. So that's how many radians we went. So the distance the plane went is this r theta. And R we figured out was 3970, the Earth 39, the Earth plus 10, times 0.2704, and so times 3970, that's 1073.6, I'll just say 1074. So 1,074 miles. The airplane is going 500 miles an hour, so it's going to take a little over 2 hours. So let's see, time is distance divided by velocity, which is 174 miles divided by 500 miles per hour. We know we did it right. The miles cancel. Hour in the bottom is like hour in the top. Divide that by 500. So I get 2.14, let's say 2.15 hours. So it took the airplane 2.15 hours to get to that latitude. Okay, to get to latitude 74 degrees, 30 minutes, 18 seconds. Okay, good. That's part A. Hooray. We are 1/4 of the way done. Okay, B, how fast is a satellite moving? Well, we already did most of the work, so this is actually a lot easier. Let's see. What is the distance of the satellite? For the satellite, we use the same formula. Theta is the same because they stay above the same place. They go the same angle. So we know theta. That was the hard part. So now we just have the radius of the satellite. The satellite is 4,800 miles above the Earth plus the radius of the Earth. So it's 8,760 miles. So its radius is 8,760 miles. So right, 8,760 miles times our angle, which was 0.2704 radians, and so we get 8760 times 0.2704. I get 2368.7, let's say 2369 miles. That's how far it went. We know it did that in 2.15 hours because they stay above each other. So the velocity of the satellite then, I'll write the formula. There we go. The velocity of satellite is distance divided by time, which it went 2369 miles. And 2.15 hours, same as the airplane. So divide that by 2.15. And I get about 1102 miles per hour. Okay, so the airplane is going about 1102 miles an hour. So then, good, so part C, that was easy. Let's see, part C, when is the plane directly over the equator and how far has it traveled? Okay, for the plane to be over the equator, it's got to go a full 90 degrees. So we do the same thing we did up here. We got to figure out the distance, which is r theta. The distance the plane goes is r theta, but now theta is 90 degrees, which we don't even have to do the math. 90 degrees is pi over 2. Pi is 180 degrees. 90 degrees is pi over 2. So the angle is pi over 2. So we know that the angle the plane goes is pi over 2. We don't have to do some crazy 74 degrees and everything. So how far has it gone? Okay, yeah, when is the plane, how far has it traveled? So the distance it goes is r theta. We know the radius was 3970 miles times pi over 2. So take 3970 times pi divided by 2, and I get 6236. So when it gets to the equator, when it's traveled pi over 2 radians, it's 6236 miles. How long does that take? So the time is distance divided by velocity, which is 6236 miles. We know it's going 500. So you can see this here. 6236 miles, time distance divided by velocity divided by 500 miles per hour. So divide that by 500. Takes about 12.47, let's say 12. I'll keep that. 12.47 hours. Okay, so that's how long it takes the airplane to get to the equator, and it has to go 6,236 miles. Now, how far, finally, part D, how far has a satellite traveled when the plane is directly over the equator? So, how far has a satellite traveled? Let's see. We know the speed of the satellite now. Another piece of paper here. So part D, how far has a satellite traveled planes directly to the equator? Okay, so let's see. The distance is velocity times time. We figured out the velocity of the satellite in part B. It's going 1102 miles per hour. And we know how long it took because it took the airplane 12.47 hours, and they go together. They're right. The satellite's always right above the airplane. So the distance the satellite goes is 1102 miles per hour times 12.47 hours. And let me see what that is. That's 13,744 miles. And that's, yep, that's about how far the satellite went. So, by just using our simple relations, that S is equal to R theta, and then the simple formulas, you know, that we've used a lot, time is distance divided by velocity, distance is velocity by time, and just thinking really carefully about circles, this problem is not so bad. The tricky part here was, again, making sure you draw your picture right, and knowing that 74 degrees is actually not very far in the first part. And then using radians really helps, makes the math simple because we can use this formula, and all we got to do is change theta to radians, everything works out. Okay, hope that helps, and thanks for listening.